Welcome back to Rice.AI Code Room. Today we are tackling LeetCode 1722, minimize Hamming distance after swap operations. In this problem, we are given two integer arrays, source and target, both of length n. We are also given an array allowed swaps containing pairs of indices. We can swap the elements in the source array at these given index pairs as many times as we want. The Hamming distance is the number of positions where the elements of the two arrays differ. Our goal is to minimize this Hamming distance. For example, if source is 1, 2, 3, 4 and target is 2, 1, 4, 5, with allowed swaps at 0 and 1, and 2 and 3. We can rearrange the first two elements to 2, 1, and the last two elements to 4, 3. The resulting array 2, 1, 4, 3 has only one position differing from the target array, so the minimum Hamming distance is 1. Let's clarify the constraints and the key insight. The length of the arrays and the allowed swaps can be up to 100,000. This means an O of n squared algorithm would be too slow. The most important insight here is that swap operations are transitive. If we can swap index A with B, and B with C, we can effectively swap A with C by performing a sequence of swaps. Therefore, these indices form connected components in an undirected graph. Within any single connected component, we can rearrange the elements of the source array into any possible permutation. For our thought process, we can use a disjoint set union, or DSU, to officially identify the connected components of indices. First, we iterate through the allowed swaps and union each pair of indices. After building the components, we iterate through the source array and count the frequencies of each element within its respective connected component. We can store this in a hash map. Finally, we iterate through the target array. For each target element at a specific index, we check if it is available in the frequency map of its corresponding component. If it is, we decrement its frequency, indicating a successful match. If it is not, we increment our Hamming distance counter. Let's look at the implementation. First, we define the basic structure of our disjoint set union inside the solution class. We have an integer vector named parent. We define a find function that uses path compression to quickly locate the root representative of an element's component. In our main function, we first initialize the parent array where each element is its own root. We iterate through allowed swaps and union them. Next, we build a nested hash map named counts. The outer key is the component root, and the inner map tracks the frequency of each source element in that component. Finally, we iterate over the target array. For each target element at index I, we find its component root. If the target element is available in our counts map for that component, we simply decrement the frequency. If it is not available, we have a mismatch and increment the Hamming distance. Finally, we return the Hamming distance. Finally, let's review the complexity analysis. The time complexity is O of n plus m times alpha n, where n is the size of the arrays and m is the number of allowed swaps. Building the DSU and processing the arrays takes almost linear time because of the path compression. The space complexity is O of n, as we need extra space for the DSU parent array and the hash map tracking element frequencies. Thank you for watching.